Welcome back, everyone. So we are continuing our Chapter 8 lecture note outline. I am right here at kind of in the first part between B and C, where we're talking the last time about the atomic emission spectra. So we looked at when we heat up a gaseous element, it emits bands of light in a line spectrum, and we learned that where those line spectra come from with the electronic transitions in energy and how that can give us some really interesting information about electrons themselves and also about the energies that they exist in and how they are quantized. So today we're going to continue with that path. And we're going to use this information that we learned about the electron, how its energies are quantized, and how we can determine the energy levels of electrons by looking at things like the atomic emission spectra. We're going to take that a step forward and see what implications that has for the electron. And we're going to actually see what form the electron will take depending on its energy level. And so the first thing we're going to talk about is the electron itself. We're going to talk about the fact that the electron is unlike a lot of things that we deal with in our everyday lives. Namely, I'm talking about the fact that electrons seem to exhibit behavior that we can't easily classify as just what we would normally consider a particle or what we would normally consider a wave. And we talked a little bit about that the last time, how there are things that we consider as being just particles and things that we consider as being just waves. And it actually turns out that electrons are kind of neither one of these things, and it's kind of hard for us to understand because we can't see them. But the fact of the matter is that there is a lot of experimental evidence showing that we can't just stick the electron into one of these two categories. So first off, let's define what I mean by a particle and what I mean by a wave. So a particle is something like a baseball or what we might consider an atom that we think of as having a distinct location in space. So we can say that particles are localized in space. So if we look at them, we know they're here, like all of them is here and none of them is anywhere else. They have a very specific location. We say this is localized. Okay, so another way of looking at this, if we draw sort of a graph where we have an x and a y coordinate, we can say, a particle has a specific coordinate and it's all at that coordinate and none of it is anywhere else. It's almost like an infinitesimal point. Now we know, of course, that there's nothing really perfectly a particle, but we can often think of solid objects as having these properties as well, even though they have volumes. Now, waves, on the other hand, are quite a bit different. Waves are not localized to one specific location in space. They're actually delocalized over regions in space. And actually, a definition of a wave is a wave is a disturbance in a field. And a field is something where it's kind of like if you had a grid where you had a bunch of possible locations on this grid where numbers could represent sort of magnitudes. A wave is really something that exists in a field like this, where we can express it as having some larger magnitudes, like a 3 or a 2 as I'm showing in this grid, or no magnitude, but it can have these magnitudes spread out over a region. And this is what we would consider to be like a wave. Like a water wave would be a really good example. If you went to the ocean or you looked at a puddle and you made a splash in that water, you could see that the wave would move outwards from the main location of that disturbance in different directions, and it would have positive magnitudes and negative magnitudes at different regions. Like, if we look at a wave that is above sort of the surface of water, like this, we say it has a positive magnitude, but if it's below the surface, it has a negative magnitude. These are called the phases of the wave. And that is something that's a very distinct characteristic of a wave as well, right? Solids don't have these properties where, say, if you throw a baseball and it hits another baseball, the baseballs don't suddenly get combined together and get larger or destroy each other and disappear completely, right? Baseballs are particles and they don't do that. However, waves do that. Right? So if you take a wave that has a positive phase and another wave that has a positive phase. And they move towards each other, and then they interact. What happens is something called constructive interference, where they join up together and they become larger. This is called interference, and waves undergo interference. Another phenomenon that you can see is if you have a positive wave moving forward and a negative phase wave moving towards that one, and they meet up, they can cancel each other out. You get zero wave afterwards. This is called destructive interference. And again, these are characteristics of waves, but not particles, right? Like you don't see this happening with any of the stuff other than waves that we see. So it's interesting. There's these particles, there's waves. Now, what about electrons? What are electrons? Well, it turns out we like to try to think of them as particles because we can count them, right? We've been doing that so far. Like if you have 3 electrons, you get a 3 negative charge, right? And you balance out with 3 protons. But it's a little more funny than that, actually. It turns out that, yeah, we can count them like units, but then, so like you could count a particle, but then they do things that are strange, like if they bounce up against each other, they can do things like constructive or destructive interference. They can bend around corners and go through places where they do things they shouldn't do, basically. So they have these particle properties and these wave properties that are very interesting and strange. And this is the domain of quantum mechanics. Now, it turns out that all waves, can be described in terms of something called a wave equation. A wave equation. A wave equation is an equation that describes a wave. And one of the symbols that's used for wave equations is this Greek symbol psi. Psi is a symbol in Greek that we use to describe a wave equation. Just like you might, if you've seen a function of x used to describe a regular function, psi is just like that. Psi is a function that describes a wave, and you can pass this function parameters just like you would any other function. Now, it turns out that we're not going to get this equation. I'm sure looks absolutely terrifying. It does, even though I've worked with this a bit, it's daunting to myself as well, and most people that are involved with this physics and chemistry together. It is complicated. The mathematics involved in describing the electron, it turns out, was developed by somebody named Schrödinger. Schrödinger recognized that what we were dealing with was an electron that has a few things going on with it. Number one, the electron behaves like a wave. Okay. The other thing that Schrödinger recognized, that it behaves like a quantized wave. Not just any ordinary wave that can have any magnitude and any direction or anything like that, but it only had specific allowed properties, like certain distinct things that we saw in the previous lesson, right, with these different energy levels. So he realized that electrons had these wave properties and they were quantized, and he was a mathematician, and he sat down and he tried to write an equation that would describe these electrons. And this is called the Schrödinger wave equation, and it's given the symbol psi. And this is a simplified form of it in just 2 dimensions, or actually I think it's one. Let me look at this. It's in the x dimension, so it's only actually one-dimensional wave equation. And it turns out the mathematics for this is advanced calculus. It falls under the domain of something called a differential equation. A differential equation is an equation that expresses itself in terms of a derivative of itself, which is all just speak for basically. This is advanced calculus. And basically, though, what we're going to look at today is we're not going to be solving this wave equation. It's already been solved for simple situations. It's been solved for most practical purposes, and we can look at the results of this equation. And it turns out when we do that, when we look at the results of solving this equation, it turns out that we can get really cool information about the electron itself and like what it's doing when it has these different energies. So if it's like around just a hydrogen atom in the ground state, we can see the electrons have one type of shape versus if we look at it in an iron where they're much higher in energy, we see that they're completely different. And we can start to understand why chemistry does kind of what it does and how bonding works in chemistry. So this is kind of a summary of what we're going to do, as we're going to consider, we're not going to solve this equation, but we are going to consider the solutions to this equation. And what we're going to find out is that each solution to this equation describes a specific wave function, which is called psi, this wave function. Now, this wave function describes something we're going to be calling an orbital. An orbital for an electron is essentially you can think of it as the probability that an electron is somewhere given some other parameters. Namely, if we specify the energy, its absolute energy, and the potential energy that it's in, we can then figure out probably where that electron would be. And if we do that over many iterations, like someone has done when they solve this, you can get a picture of what the electron is doing when it has a specific energy. It will also describe, when we solve this wave function, the size, the shape, and the geometry of that electron, because it describes the orbital, which is describing that. So what basically we're going to do is we're going to look at the solution to this wave equation when each of the energy levels that we looked at on the previous lesson, where n is equal to 1, 2, or 3, where this principal quantum number goes from low to high, we're going to see the different solutions to this wave equation and what those look like. And we're going to learn about them in terms of, they're called orbitals or subshells of these shells. Okay, so let's go take a look at how that works on the next page of the notes. So there's a little bit of terminology that we're going to start using quite a bit, so we need to make sure we sort of make sure we're all on the same page as far as that terminology. We're going to be using the word shell, subshells, and orbitals quite a bit for the rest of this lesson. So let's talk about what those words mean. Now, you might remember from the last lesson, we looked at the different energy levels for an electron by looking at the line spectra. So we said, okay, if we look at the line spectra for hydrogen, we see these different lines, and they have different colors. And we learned that from those different colors, we can determine different energy levels for the electron. So let's draw a picture kind of summarizing some of that information, right? We have the center of the atom, the nucleus, and then the electron itself can exist at these different energy levels outside of the nucleus. And we gave those energy levels a name, right? A symbol. We said that they have principal quantum numbers, where that's the n, and the n increases from 1 till essentially infinity. Now, these different principal quantum numbers can be used to solve psi, the wave equation, and they represent essentially shells. These are energy shells, but when you solve the wave equation for each of these shells, you get essentially what we call a subshell. Different ways that the electron can exist depending on what energy level it has. And the higher the energy level of the shell, the more possibilities the electron can have, because that electron has more energy in those higher energy shells. The lower energy shells have less of these subshells, and the higher energy shells have more of these subshells, okay? So the first, kind of summarizing that, we've got this thing that we're calling a shell, right, around here. And these are the different shells. So we have shell 1, shell 2, shell 3, and shell 4. Now what we're going to do down here is we're going to, and for the next page or so, is we're going to look at each of these shells. We're going to start the lowest energy one, and then go to the next, and then the next, and then the next. And we are going to look at the solutions for the electron's wave equation at each of those shells. And we're going to see, what is the electron's possibilities when it's in those shells. So I'm going to show you the solutions to the wave equation. We're going to learn that in each shell, there may or may not be more than 1, 2, 3, or 4 different subshells. These subshells will contain what we're going to learn to call orbitals, which are specific probability kind of shapes or volumes, you can think of them, for the actual electron. And we're going to go through each of those in turn, okay? So let's get started. Let's look at the first shell. So the first shell is the one where our principal quantum number, n, is equal to 1. So for n is equal to 1, we're talking about the lowest energy shell here. This is when the electron, if there is one in this shell, it is the lowest possible energy you can have. So at this low energy, when you solve the wave equation for this electron, where n is equal to 1, this doesn't give a lot of options to the electron. It's in a pretty low energy state. And for that reason, there's actually only one possibility for this electron, or one subshell. And we also call this subshell a type of orbital. So we only have one type of orbital here at this n is equal to 1. And we give it a name, this subshell or this type of orbital. It's called an s orbital. Okay, so this subshell is called the s orbital. Now, we're going to talk about what that means here in a minute. But an electron in one of this n is equal to 1, can really only be in this 1s orbital. And we actually write it down like that. So when we write these down, we provide, when we're describing an electron in a specific place like this, we would say it's in n is equal to 1 and it's in the s orbital. So we actually write it like this, like 1s, where that 1 there, that represents the shell that the electron is in, and the s represents the subshell that it's in, okay? We're going to see actually later that when you have other types of subshells, that's kind of important. Now, what does this s orbital actually look like? So you can actually plot or look up 3D plots for this. I've actually done this by hand when I took physical chemistry and we solved the wave equation. When you actually plot where the electron is at this energy level, it turns out that it ends up producing a plot that looks like a sphere. So you've got the nucleus in the center of a sphere, and then the electron outside of the nucleus in a spherical region. And that spherical region is kind of, you can think of it almost like a cloud where the electron can be. It's not necessarily at any one place in that sphere, but it's delocalized all over it. Now let's go to the second shell. Now the second shell is where n is equal to 2. Okay, and what happens here is we're at a higher energy level. So when we have n is equal to a higher energy level electron, you solve psi for this, the additional energy basically provides more than one quantum state for the electron. When n is equal to 2, we actually get two types of subshells. So we get two subshells here. One of the subshells is an s-type, so we see that s orbital again. Of course, it's at a different energy level, but there's one of them. We have one type of s orbital, but we also see a new type of subshell. And this new type of subshell is called a p orbital. And it turns out we actually get 3 distinct p orbitals at this energy level. So if we were describing these with symbols, we would say at the second shell, we would have a 2s orbital, and we would have 3 2p orbitals. Now, notice a few things before we continue forward with this. Notice that I have the 2 written in front of the s orbital. That's to say that this is at n is equal to 2. And then we have the s orbital. This describes a 2s orbital, which occurs at the second shell. But also in the second shell, we get 3 of these new things called p orbitals, which I'm going to show you what they look like here in a minute. But also notice there's an x, a y, and a z subscription next to them, okay? And that's because we have these 3 different types of p orbitals, and it turns out that this x, this actually comes out of the equation when you solve it, this x, this y, and this z. Those describe the orientation in 3-dimensional space of these different p orbitals. So, like kind of summarizing here in this, when we're solving this wave equation for n is equal to 2, we get these 2 different types of orbitals. We get s orbitals and p orbitals. And it just so happens there are 3 types of p orbitals, but only 1 type of s orbital, okay? So let's write all that down. So kind of summarizing what we just talked about. At the subshell where n is equal to 2, we find that the wave equation tells us there are two subshells, or two types of orbitals. There's the s type and the p type. Okay, so s orbitals and p orbitals. These are subshells, the s subshell and the p subshell. Now the s subshell, there's only one type of s, okay? But the p subshell produces three types of orbitals. These are p orbitals, px, py, and pz. Now you're probably curious what these p orbitals look like. Let's talk about that, actually. P orbitals look pretty neat. I actually have a set of models for p orbitals in my office, or someone else is borrowing them. If you ever want to stop by, take a look, they kind of look like this. Each p orbital that we have, we have three different types, each p orbital actually has two lobes, okay? And those lobes I'm sort of highlighting here. We're going to talk about why these are called py, px, and pz, but basically if you look at them, you'll notice they're all 90 degrees from each other. Now we're going to actually draw them, and I want you to draw them with me in this box up above. We're going to look at each one, what they look like, and then we're going to compare that with the 2s orbital as well. So let's first start when we're drawing these p orbitals by getting some three-dimensional looking coordinates. So we've got an x, a y, and a z axis on our little graph here. And I want to draw the px orbital first. And you'll notice those lobes, which I've just tried to draw there in blue, those are oriented along the x-axis. That's why we call it the px orbital. Now, if you solve the wave equation and you get the p orbitals, you'll find there are three of them. There's another one at py, and this is where the lobes are oriented along the y-axis. And if you do this, you will find that you also have a pz orbital, where the lobes are oriented along the z-axis. So each of these p orbitals is 90 degrees from the other type of p orbital. Now, what about the s orbital? Well, the 2s orbital, s is always a sphere, and the 2s orbital is just a larger sphere than the 1s orbital. So I'm drawing a 2s orbital here, and I'll draw these aren't to scale, but it's approximate, and then a 1s orbital next to it. Notice the 2s orbital has a larger radius. It's bigger than the 1s. That's basically the difference between these two. And you can imagine like an atom. If you had an atom that has electrons going sort of in the 1s orbital, but you have some in a 2s orbital, and then maybe also some in a 2p orbital. This happens, right? Like oxygen has this situation. It has 1s electrons, 2s electrons, and 2p electrons. It turns out that all of these, you can kind of think about these orbitals as places around the nucleus where the electron is, and they're all superimposed on each other. So if you sort of combine them all, you might have kind of a picture of what it might look like. For instance, like if you had a nucleus here and it had some electrons in the 2s orbital, those might be out here, in the 1s orbital, and then outside of that there might be electrons in like a 2s orbital, and then there might be also some electrons in a p orbital, or more than one p orbital, right? And they're all sort of in this thing together, right? These aren't separated in space around an atom. The nucleus of the atom is always right in the middle of these things. So for a p orbital, the nucleus of the atom is right between these lobes right here, okay? Like right here, and right here. In the s orbital, it's right in the center of the sphere, okay? And then all of these are superimposed on each other in space. And we're going to actually look soon at different atoms, what types of electrons it has. So we're going to look at, for instance, nitrogen. We'll look at iron, and we'll say, well, iron has 58 electrons or whatever. Where are they, in what orbitals are they in? Okay, so that's what we're going to be looking at kind of moving forward. Now, we haven't finished looking at the shells yet, so let's go to the next page. We'll look at the third and the fourth shell and see what happens there. So in the third shell, this is where the principal quantum number n is equal to 3. We are at a much higher energy level, and for that reason, the electron in one of these shells has a lot more options, and it turns out it has three types of options, three types of orbitals, or three subshells. It has the s type, and we have one of these, and this is the 3s orbital. There's one of those. We also see p show up again, and we get 3p orbitals. We would get the 3px, the 3py, and the 3pz. Now these look like the other p orbitals, they're just larger. Okay, but we also get a new type of orbital here. We get something called the d orbital, and it turns out there are 5 of these d orbitals. Okay, these are the 3d orbitals, and d orbitals always come in 5s. So if we summarize here in this n is equal to 3, we get the s, the p, and the d types of orbitals. Now, what do these d orbitals look like? Well, we're not going to actually draw them, but these are, here's some graphics showing you kind of what they look like. There are, like I said, 5 types of d orbitals, and they look a lot like kind of like a 4-leaf clover, some of them. So they have like a p style set of lobes, but instead of having 2, it turns out that they have 4, like this. And depending on what axis those are at, if they're all on an axis or they're in between an axis, they are given different symbols, like 3dz squared or 3dxz. So you'll notice 3dxz here. If we kind of look in a little bit closer, you'll notice the lobes are oriented in between the x and the z axes. So it's like we have them in between these. Whereas if you notice here for 3dx squared y squared, that the lobes are actually oriented, both of them, directly on those axes, the x and the y. Okay, so we get either between the axes or directly on them. That's the basic idea with it. So there's also this kind of funny looking one here. It looks like a toroid with a p orbital in the middle. So you have this sort of ring going around a p orbital. Now remember, on all of these, the nucleus of the atom would be in the center of these orbitals. And these are very large compared to, like, the volume that they take up is rather large. So if you think about this in terms of scale, the electron would be somewhere, if it's in one of these orbitals, compared to the nucleus, it's something like, if we put the nucleus in California, the electron at the edge of one of these would be in, like, New York. So it's very far away from it. It's a huge distance. Okay, so that's those are the d orbitals. Now, I'm not going to have you drawing the d orbitals, but I do want you to be able to recognize them when you see one. Okay, so let's move on to the 4th shell. So the 4th shell is when the principal quantum number n is equal to 4. And you might have guessed by now there's a little bit of a pattern here. If we have n is equal to 4, we should have 4 types of orbitals. So that's a pattern you might have recognized, and it holds true actually with the math. The principal quantum number will define the number of the number of subshells, or the number of types of orbitals that you have. So here we have 4 types of orbitals. We have the s, the p, the d, and a new one called the f orbital, which I've drawn. One of them is over here in this box. We're not going to draw these as well. But notice that you have twice as many lobes as we saw in the d orbital. So let's summarize here. We've got 4 types of orbitals. We have the 4s, we have 1 of those. We have the 4p, we have 3 of those. The 4px, the 4py, and the 4pz. We also have the 5 of the 4d orbitals, and we have 7 of the 4f orbitals. And the f orbitals, they're quite complicated. These are all of them here. We see a similar pattern as we did with the d orbitals, where they're oriented along different axes, and then we get this toroid-looking one, fz cubed up top. Now, actually, if we went beyond this in terms of n is equal to 5 or n is equal to 6, and so on, well, you can get other types of orbitals. Now, we don't have a lot of experience with atoms, elements, I should say, that exceed this energy level, but we do have computational models which show the types of orbitals. So if we went beyond n is equal to 4, like if we went to n is equal to 5, we would have 5 types of orbitals, and we would call those new ones g orbitals. And if we went to n is equal to 6, we would get also h orbitals. And these are theoretical, these g and h orbitals. So it's kind of an interesting thing. You'll notice also that the letters of the type of orbital. So we started with S, then there's P, then there's D, then there's F, which it might not make a lot of sense. Like it does make sense from here. It goes like F, A, B, C, D, E, F, and then it goes G, H, and then it would be I, J, etc. It just follows the alphabet after this. But why the S, the P, the D, and the F? It turns out that those letters come from the original analysis of the line spectra that we were looking at yesterday. So actually, if you look at the line spectra very carefully, you can pinpoint certain patterns in the line spectra themselves. And these S, P, D, F letters are symbolic of certain things that we're seeing, such as S meant specific, P meant principal, D means diffuse, and I believe F was fine or fixed. I can't remember, actually. But anyway, these letters had different optical property meanings with respect to the line spectra. So that's some information about that. And then after F, it just follows the alphabet. Again, these are all theoretical, though. We're going to be dealing with, in this class, we're going to be focused mostly on S and P orbitals. We will occasionally talk about D orbitals, and very, very rarely will we talk about F orbitals. And I don't expect you to know the different axes that the D or the F orbitals. So this stuff here, don't expect you to know that. I do want you to know about the different shapes of the S, the P, and the D orbitals, and then that there are 3 P orbitals, of course, and 5 D orbitals and 7 F orbitals. And I do want you to know that the P orbitals, the 3 of them, are 90 degrees. So there's an X, a Y, and a Z one. That's basically what I want you to know about the orbitals themselves as far as their nomenclature is concerned. And I also, of course, want you to know how many orbitals at a different subshell, okay, which that's some pretty basic stuff. We're going to go to the next page now and look at how these are organized. We're going to sort of organize them and kind of look at where they're placed in terms of their shells, but also then we'll look in terms of their energies. So let's go to the next page and take a look. Now, before we get too far ahead of ourselves, let's take a step back and talk about what we're doing with these orbitals. What are we trying to accomplish here? Well, what these orbitals are again, they're solutions to this wave equation, but what's that mean? Really, all these orbitals are descriptions of the electron. We're trying to describe what the electron is, where is it, with the hope that maybe it will tell us something about how chemistry works, because chemistry is fundamentally all about what the electrons are doing. So these orbitals are one description of that, and so far we've learned that the some things that the orbital tells us through this wave equation, right? This helps us figure out, like, if we have a given energy for an electron, which we are assigning this n, n is equal to 1, 2, 3, or 4. This describes the energy of the electron, and so that's one parameter about it. It says basically how far away from the nucleus is it, what's the state of this electron. Another thing that we're using to describe the electron is the subshell. Okay, so the subshell. And the subshells we learned about are S, P, D, and F. What does the subshell information tell us? Well, the subshell information tells us essentially about the shape that the electron is in, the region of space that it's in, as a three-dimensional model. Okay, so that's what the subshell tells us. We also learned about the orientation in space of these. So we learned about the coordinates, like the X, Y, and the Z portions of the P orbitals, for example. This tells us about the angle that it's oriented along. So it's kind of shape also. So both of the shell and the angle, I'll write this, the angle, tell us something about the shape of the electron. Okay. Now these aren't the entire things that we need to completely describe an electron. It turns out there's one more thing that we're going to need to use to describe an electron, and it turns out that it actually doesn't come out of the wave equation. It was discovered or sort of theorized first by somebody named Pauli. And we're going to talk about Pauli later, so that's why I wanted to bring up his name right now. Pauli sort of theorized about something called electron spin. And that turns out to be the last piece to at least our description, or quote unquote complete description of an electron. It needs to take into account its spin. And the spin, it is analogous to what you would think of like a spinning sphere or something like that. Really what it is, though, is a magnetic moment that the electron has. And it turns out there's an experiment that demonstrates that electrons do in fact have this spin that Pauli theorized before the experiment was done. And it turns out, just like Pauli thought, that the spin of an electron, which I'm demonstrating with this picture here, can be only one of two spins, where it's spinning like this, where we have this anti-clockwise spin, and then we have this counterclockwise spin, regular clockwise spin like this. And when the electron has this spin, it generates magnetic field around it. And it turns out only two spins are possible for an electron, either up spin or down spin. And it turns out this spin is quantized. So an electron can go between these two different spin states instantaneously, but nothing in between. There's no spin like over here or over here. It's either this axis or up and down, or this, where north is up here and south is down here. So there's only one of two spins, spin up and spin down. There's no spin sideways, for example. Okay, so I'm just going to write that down here. And this is important, especially a little bit later. We're going to find out that spin helps us figure out something really important about how electrons are surrounding an atom, okay? So let's just summarize all of this. This one where we have the arrow pointing up, we call that the upspin electron, and we usually symbolize that with an arrow pointing up for obvious reasons. There's also the opposite spin, which is, we call that the downspin electron. And of course, for that we use an arrow that's pointing downwards. Okay, so an electron can only have one of these two spins. Now what we're going to do below is we're going to organize what we've just learned about all of the different shells and subshells in a chart. So I'm going to draw a chart here where we're going to have on the column on the left over here the different shells. And the shells are labeled by their principal quantum number, n. So I'm going to list from n is equal to 1 up to n is equal to 4. And then on the right side of this table, I'm going to show the subshells that are possible at each of those shells, just to kind of keep track of what we have at each of these shells. So let's do this. We've got n is equal to 1, n is equal to 2, and then we have n is equal to 3, and n is equal to 4. Now, what are the subshells at n is equal to 1? Well, at n is equal to 1, we have S. At 2, we have S and P. At 3, we have S, P, and D. And then at 4, we have S, P, D, and F. Okay? So let's write these out. At n is equal to 1, we have the 1s. At 2, we have the 2s and the 3 2p orbitals, the px, the py, and the pz. Okay? At n is equal to 3, we have the 3s. We have just one of those. And then we have the 3 p orbitals. There are 3 of those, px, py, and pz. And then we have the 5 3d orbitals. So we have 3d, and there are 5 of those. And then at n is equal to 4, we have 4 types of orbitals. We have the 4s, the 4p, and there are 3 of those. We also have the 4d. Of course, there are 5 of those. And then finally, we have the 4f orbitals. And remember, there are 7 of those. Okay, so these are all of the different orbitals that we have, organized by the type of shell that they're in. Now, what this doesn't show, actually, is the organization of these orbitals according to their energies. It just shows them organized according to the type of shell energy that it has. But the individual orbitals themselves also have an energy associated with them that varies depending on a lot of different factors. We're going to kind of keep it simple, but we do want to know basically where these things fall in terms of their energies. That way we can predict when we're looking at, say, an iron atom, are the electrons that are the highest energy ones in a d orbital, or are they in a p orbital? What type of orbital are they in? Because that will change their shape dramatically and probably their chemistry as well. So let's go to the next page, where what we're going to do is organize the orbitals according to their energies rather than just by the shell alone, okay? So let's go take a look at that. So we're going to start by drawing out a line on the left here showing the energy so that we can place the orbitals by their energy levels. So the top is going to be high energy and the bottom is going to be low energy. Now, as a consequence of their distance from the nucleus, the individual orbitals themselves have an energy ranking where S is the lowest energy, followed by P, followed by D, and followed by F. And this is only for, when we're talking about this, it's only for when we're comparing orbitals in the same shell. So for instance, a 2p orbital would be higher in energy than a 2s orbital, okay? A 3 or a 4s orbital might be higher for sure than like a 2p orbital, for example. Another principle here is that the lower the n, the lower the energy. Now here's a little tool that you can use to help you come up with this information if you have trouble sort of remembering it. Now, it turns out you're going to see soon enough that the periodic table contains within it all of the stuff I'm about to show you. So if you know how to use the periodic table, it unlocks all of this. So you won't need to use this necessarily, but it's a good place to start. So what I'm going to draw here is a little tool where I want you to draw this as I'm drawing it. The first thing you're going to do is you're going to draw a column of numbers going from 6 down to 1 vertically. So 6, 5, 4, 3, 2, 1. And then you're going to have a column next to it where it's going to be 6, 5, 4, 3, 2, and then don't draw a 1 down here. So leave that blank. And then you're going to have a third column where it's going to go 6, 5, 4, and then 3, and then 6, 5, 4. And we're going to go and make 4 columns of these. We're going to make one for the s orbitals, one for the p orbitals, one for the d orbitals, and one for the f orbitals, okay? So let's go ahead and do that real quick. So my third column here is 6, 5, 4, 3, and then 6, 5, 4. Now I'm going to put the orbital symbols next to each of these numbers. So the first column is s orbitals, the second column is p orbitals, the third is d orbitals, and the fourth is f orbitals. Now you might be wondering, what am I going to do with this little table? Well, it turns out that this little table, this device that I've drawn, the way it's set up will actually, if I know how to use it right, will allow me to predict which orbitals have lower energies and which have higher energies, and the sequence of those orbitals in terms of their energies. So it basically will allow me to organize the orbitals by their energy. And the way it works is we're going to start down here at the bottom, and we're going to see that, of course, we already know that the n is equal to 1 is the lowest energy, and s is the lowest in that shell, and that will be the lowest energy orbital. Okay, and that will be followed by the second shell, which is n is equal to 2. And so we're going to see that the lowest energy orbital in as n is equal to 2 is 2s, and that will be followed by the 2p orbital, okay, followed by the s orbital, followed by the 3p, 4s, and so on. And we're going to see there's some interesting anomalies in there. So let's go ahead and I'm going to show you how to use this chart to organize these orbitals by their energies. So I'm just going to zoom in a little bit so I can draw these, and make sure you draw kind of small on your table. So we're going to start down here, and we're going to see that the first thing we run into is a 1s orbital. So I'm going to draw 1s down here at the bottom. Then we're going to see there's a 2s after that, so that's 1 up above it. And then we get to the 2p orbital. Now remember, there are 3 of these p orbitals, the 2p. So let's draw 3 of them there. Those are all at the same energy level. Notice here that this is predicting so far, for the first and the second shell, the predicted energy levels for these. So 1s at the bottom, followed by 2s, followed by 2p. Well, what comes next? Well, next is the third shell. So what's the lowest energy orbital in the third shell? It's the 3s orbital, which we see is right after the 2p on our chart. After that, we get 3p, and there are 3 of those. followed by 4s. So you can see the energy jump from 2p to 3s, and then 3p, and then 4s. So this is the first, second, and third shell, and part of the fourth shell. What comes after 4s? We see that this chart predicts 3d. So 3d is after 4s, and that actually completes the third shell, right? So we have the 1s orbital, then and that's in the first shell, and then the second shell has the s and the p, and then the third shell has the s, the p, and the d. So notice here that the 4s orbital is lower in energy than the 3d orbital. So we need to actually complete our fourth shell here. So what comes after the 4s? Well, if you look at the chart, after the 4s comes the 3d, and then the 4p, and then the 5s. So this is the jump in energy up to 5s. And what's after 5s? Well, we see the chart predicts a 4d, and there are 5 4d orbitals, so let's draw a line for each of those. And then we see after 4d, which is right here, the next orbital that we encounter is 5p. So 5p will be higher in energy than 4d. So let's write that. And remember, there are 3 of those p orbitals. So what's after 5p? Well, we have 6s, and there's 1 of those. And then we get to 4f, the f orbital. Now remember, the f orbital, there are 7 of those. So 4f, and I'm going to draw 7 lines representing those. So we see it goes from 5s to 4d, then 5p, then 6s, and then 4f. Okay, what's after 4f? So let's take a look at the chart. After 4f, we see it goes to 5d. So let's write 5d, and remember there are 5 of those orbitals. So it goes from 4f to 5d, and then it goes to 6p. 6p has 3 orbitals, so it's px, py, and pz. And then we go to 5f, and then 6d. And I'm running out of space here at the top. Maybe you drew a little smaller or closer space to each other, but the final orbital way up here would be the 6f orbital, which is above 6d. So I'm just going to draw those lines there. There are 7 of them. And the energy jumps go like this. So it's like 4f to 5d, then 6p, then 5f, then 6d, and then 6f, okay? So there's a lot of orbitals. Now, this scheme actually of the energies, if you put the number of electrons that can possibly fit into all of these orbitals, actually accounts for all of the known elements that we have. So we're going to be able to figure out for any element on the periodic table what the layout of electrons are in each of these orbitals. And we're going to learn some principles about how to do that. Specifically, we're going to do that in the next lecture. We're going to learn about different principles we can apply, such as where do we put the electrons in what order? And we're going to find out that we're going to fill these orbital energy diagrams from the lowest energy to the highest energy. And then we're going to learn also that any given orbital can only hold 2 electrons. And that has to do with the spin of the electrons and how they have to be opposed rather than paired. So that's what we're going to do in the next lesson, and we're going to do some sample elements and come up with their electronic configurations, where the electrons are. So with that, I'm going to end today's lecture. Thanks for watching. Let me know if you have any questions. Take care.